So, hi everyone. Today I'll be presenting the paper on comprehensive memory safety analysis of bootloaders. None of the authors could make it to the conference, so I'm presenting on their behalf. So let's take a step back and look at what happens when you click on power on button for a computer. There are three major steps that are happening. First, either your BIOS or UEFI firmware gets executed by the processor. This is mainly responsible for loading the bootloader image, and then the bootloader starts its execution. This bootloader may or may not have an interactive shell, and finally, this bootloader is responsible for loading the OS image and then finally handing over control to the operating system. The story of this paper is mainly involved with the bootloader execution. But now, why bootloader execution? So if we look at our secure boot chain, bootloader execution plays a very crucial role. So each component in secure boot verifies the upcoming component. So your BIOS in UEFI is responsible for verifying the bootloader. The bootloader is then responsible for verifying the OS kernel. So now, if the bootloader during its execution gets compromised, then you can completely break the system security. You can load a malicious OS, and then your security guarantees are out of the window. So the bootloader plays a very crucial role in secure boot. So in order to analyze bootloader security, we went through 85 existing bootloader vulnerabilities. We classified these vulnerabilities and looked through common patterns. And now, if you'll categorize these vulnerabilities by attacker capability, you'll find three primary types of attackers. Attackers which can attack the bootloader with physical access, attackers which can access it with remote access, or finally, some of the vulnerabilities were context-dependent vulnerabilities, not always triggerable, but only in certain circumstances. Now, if you again look at physical access and remote access-based vulnerabilities, you'll find that there are three prominent sources. So these vulnerabilities can mainly arise from interaction of bootloader execution with the storage peripheral, the network peripheral, or finally with console. So these are three prominent sources behind these vulnerabilities. Again, if we reclassify these 85 vulnerabilities, we see a very strong pattern that 91% of these vulnerabilities are arising from storage, network, or console. So this kind of gives us a hint about these three sources are very prominent sources for vulnerabilities in bootloaders, and maybe we should look with more scrutiny towards them. Before going ahead, let's define the threat model. So the main goal of the attacker is to compromise bootloader execution by exploiting memory corruption vulnerabilities. Now, what can and cannot our attacker do? We assume that our firmware and bootloader image cannot be tampered. Normally, it's signed, and we assume that forging these signatures is a difficult task. Then, the attacker cannot also influence the CPU and memory directly. And finally, attacker cannot also influence persistent storage, for example, NVRAM variables. On the other hand, we do assume that the attacker has limited access to storage data, network data, and console data. What do we mean specifically? So in terms of storage, the attacker can go to the computer and then physically plug in a malicious USB drive. In case of network, many of these bootloaders interact over network, and then our attacker can inject a malicious network packet into bootloader execution. Finally, in order to interact with the console, what our attacker can do is just plug in a keyboard into the device and then inject malicious commands into the console. Next, which targets were evaluated in the paper? So in the paper, we evaluate 9 different bootloaders. There are 3 selection criteria for selecting these 9 bootloaders. First, the bootloader should be open source. Second, it should be actively maintained over past 2 years. So if the bootloader is old, then we don't take it in our evaluation. And then finally, we select the latest version that was available for that bootloader at that point in time. You can see these 9 bootloaders use a lot of different targets, and then it also includes GRUB, which is commonly used on Linux systems. Let's take example of GRUB to see things more clearly. So in case of GRUB, what we can see is GRUB has all 3 types of sources that we have previously talked about. So GRUB also interacts with storage peripherals. It also interacts with network peripherals. And finally, GRUB also has console. So now, in case of GRUB, our attacker can inject packets or can try to exploit the bootloader from all three of these sources. And given that there are a large number of file systems, partitions, and network stacks supported by GRUB, this increases the attack surface. And normally, as we have already seen, a large attack surface leads to a large number of vulnerabilities. If we look at different bootloaders, we find similar situations. So now, in case of Lemine and U-boot, we also see they support different types of partitions, different types of file systems, and again, different type of files on the top of the file system. So there are a lot of different layers in this thing, and a large number of source code is attached to that thing. Because your OS has not started its execution yet, the libraries are not there, and your bootloader is responsible for parsing and processing. So everything must happen inside the bootloader, and the bootloader contains all the code for processing these things. Now, if we look at the network stack, there's also a similar situation. A few bootloaders have their own complete network stack. A few don't have complete network stack, but only certain parts of the network stack. But again, large code base, large possibilities of vulnerabilities. Finally, in case of console, this is a little bit straightforward. Some of the bootloaders support injecting inputs via console. For example, here we can see GRUB. GRUB has a very simple interface where you can go in and type anything. Now, if you are an attacker, you can type malicious things. And if you're not parsing these things nicely, mistakes may happen. So now let's talk about the fuzzing framework that we devised for testing the bootloader. Essentially, the bootloader is run inside a virtual machine. And then we trigger different file, network, or console operations. As soon as these three types of operations are triggered, they normally access the peripheral. As soon as a peripheral access is triggered, fuzzer-generated input is passed to the bootloader. At the same time, Intel PD is used to collect coverage. This coverage is passed on to the fuzzing engine to inform the fuzzer about interesting inputs and discarding non-interesting inputs. So let's look at it in a bit more detail. So what do we exactly mean by the storage operations on the last slide? So in case of testing storage operations, what we do is we discover different partitions that are available, then we mount the file system, then we open the file system, and finally we read, write, or delete files from the file system. And finally, the partition is unmounted. And what happens at this point is fuzzer-generated input is injected as soon as the storage interaction leads to the peripheral interaction. So these fuzzer-generated inputs are then used by the bootloader execution, and then it may or may not break the bootloader execution. In case of network, we go about discovering the network interface, then we send or receive packets over this interface, and then we process these packets, and finally the network interface is closed. In this process, during sending and receiving of packets, the bootloader uses fuzzer-generated inputs. And finally, in case of console operations, we again invoke different console functionalities and inject fuzzer-generated input into the console. Now, let's talk about crash detection. So we implement 4 different things to facilitate crash detections and to decrease false positives. First, BIOS-based bootloaders don't implement paging by default, so we implement paging so that at least invalid memory access leads to an exception, and then we can at least try to catch that something wrong has happened. Then we also insert custom hooks, as soon as custom hooks for handling the exceptions. So for example, if a divide by 0 happens somewhere inside the firmware, then these custom hooks catch these exceptions and tell our fuzzer that a crash has happened. And then our fuzzer knows, this input was interesting, let's keep it in our corpus, we'll reuse it later. Third part, we also have panic hooks. So sometimes the bootloader understands that something wrong is being entered, and it panics. And instead of telling the fuzzer that this is also a crash, we tell the fuzzer, look, the program has exited nicely, because there's no use in using panics as crashes, because this will lead to false positives. Finally, we also add a simple heap sanitizer to the bootloader. So what we do is we add red zones. So 8 bytes are added during allocations, and then during deallocation, we verify these 8 bytes to see like if there was a heap overrun or not. And these 4 techniques help us in detecting crashes across the bootloader execution when fuzzing is happening. So what do we find? We find 39 new vulnerabilities. 29 out of them, 29 have been either patched or confirmed. For more details, I'll refer you to the paper. There's a complete table inside the paper. Then let's compare it against other tools. Since there's no ready-to-use bootloader fuzzing framework out there, we compare our bootloader fuzzing framework against existing static analysis tools. We specifically choose CodeQL and Clang Static Analyzer for the comparison. And if we look at the table, what we specifically see is like in case of static analyzers, there are a large number of reports, and then the true positive cases are low. In comparison, for our fuzzer, what we see is the number of generated reports are also small, and most of them are true positive. So we have less false positives and a large number of true positive reports. In conclusion, we identify 3 main attack surfaces which can be used to compromise bootloader execution and overall break the guarantees of secure boot. First, we analyzed 85 existing CVEs to understand this attack surface. Then we developed a fuzzer to specifically look through these 3 sources and perform a fuzzing at this layer. In the end, we discovered 39 vulnerabilities, 5 CVEs were assigned, and 29 were confirmed or patched. And finally, this highlights a critical area of concern in bootloader security, and we hope that this tool will facilitate more research in case of bootloader testing, and also will facilitate the developers in finding vulnerabilities faster. Thank you. And if you have any questions, please contact the paper authors. Because I can't answer the questions.
All right. So let's thank the presenter one more time, okay?